Welcome everyone. Today I'm going to be doing an Exam 1 review for chemistry. Now here are the topics listed that I'm going to be doing questions on. Now as we go through this video, my suggestion is that you pause the video as we get to every new question and you try out the problem on your own before replaying the video and seeing what the solution is. I have linked the periodic table in the description so you can use that as we go along. If you're new here, my name is Liah, and on my channel you can find more science and math tutorials. Now, because this is an exam review, I'm going to just briefly go over the topics, and I'm not going to go over an in-depth explanation of each. Okay, I have tutorials on separate topics for that. Alright, with that said, let's get started. Here I have question number 1. So, how many meters are in 69 kilometers? So in this question, we need to go from 69 km to meters, which is just m. So what do I know about kilometers and meters? Well, I know that there are 1,000, aka 10 to the 3, meters in 1 kilometer. Alright, so that is from the metric unit conversions chart. You can find those online if you just search them, okay, SI units. And so these are the equivalents, okay? Now, let's get started on converting this. I'm going to convert 69 km to meters. Now, how will I do this? Well, I need to cancel out kilometers, so I will put the unit of km on the bottom and meters on the top. And I will put the corresponding numbers. So I have 10 to the 3 meters, and I have 1 kilometer. Kilometers on the top and bottom, these cancel out, leaving me with meters, which is what I want. Now, if you just do 69 times 10 to the 3, aka 69 times 1,000, you will get 69,000. Okay, you just kind of add 3 zeros there. So in the end, our answer is that 69 kilometers is equivalent to 69,000 meters. What is the volume of a block of a metal that has a density of 10.49 grams per centimeter cubed and a mass of 30 kilograms? Alright, so what am I trying to find? Well, I'm trying to find volume. Now, shortcut is that I use this little circle and I cover up the unit I want, which is volume, and I am left with volume equal to mass over density. Alright, so now that I have my equation for volume, I can just go ahead and plug in numbers. Alright, so I will continue this. So in the top we will have mass. What is that mass? Well, it's 30 kilograms. What is the density? The density is over here, 10.49 grams per centimeter cubed. So looking at this should raise some, one big red flag, all right? And that is because we have kilograms on the top and only grams on the bottom. Now, we cannot do the division straight away. We have two choices. We can either convert this many kilograms to grams, or we can convert this many grams per centimeter cubed to kilograms per centimeter cubed. So I'm just going to convert everything to grams, so I'm going to convert this one to grams. So I'll do 30 kilograms, and we want to convert to grams, right? So in my new fraction, I'll put kilograms on the bottom, grams on the top, kg cancels out, and then I have these equivalents. So I have 1,000 grams in 1 kilogram. And then here I know that this is going to be 30,000 grams. Okay, so instead of kilograms, we're going to have 30,000 grams. So now we do this division. So 30,000 divided by 10.49. This results in 2,859.87, and this unit will be in centimeters cubed. So this is what our volume is. A rocket is traveling at 500 miles per hour. What is its speed in kilometers per second, given that 1 mile is 1.609 kilometers? So this is a dimensional analysis problem. Alright, so what do we have? We have this rocket is going to be traveling at 500 miles per hour. So 500 in 1 hour. Okay, and I'll just put HR for hour. And then what is its speed in kilometers per second? So then we want to convert this to kilometers per second. S is for seconds. So clearly, right, the differences in length and in time need to be converted, okay, so that we get our desired units with kilometers over seconds. So this problem is very similar to the first problem, or the first two problems, about converting units. It's just that for dimensional analysis problems, you'll likely have to convert 2 units instead of 1. So in this case, we're converting the units for length, and we're also converting the units for time. So with that in mind, let us start converting. So we have 500 miles per 1 hour, and I'm going to go ahead and convert length first. You can convert time if you want first. You will get the same answer. All right, but I'm just going to do length first. So I have another fraction, and this fraction here is going to be used to cancel out miles. So I'm going to put miles on the bottom. And what am I converting to? Well, I'm converting to kilometers. So I'll put kilometers on the top. All right, now I will put the numbers here. Now I will use what the question says. So 1 mile is going to be equivalent to about 1.609 kilometers. As you know, miles on top, miles on the bottom, you get to cancel them out. All right, and then I'm going to convert my time because my kilometers match what I want in the final answer. So let's go on to convert time. So I need to convert hours to seconds. Now, I know that in 1 hour, there are 3,600 seconds. Okay, and so I can say I want to cancel out hours, so I need to put hours on the opposite level of what it is originally. Okay, so 1 hour has 3,600 seconds. Hours will go away, and I am left with seconds. Okay, so now I can just multiply everything out and get my new fraction. When you do this division and multiplication, you're going to get 0.22 km per second. This is another dimensional analysis problem. So a swimming pool was filled with water at 80 liters per minute. How fast is the pool filled up in milliliters per hour? And then another question here is how long in minutes will it take for the pool to contain 850.47 liters? Okay, there is a lot to unpack here, so let us answer one question at a time. So starting with what we know is that we are going to fill this pool up with water at 80 liters per 1 minute. Okay, very good. And we need to find how fast this is being filled up in milliliters per hour. So here we're going to convert the volume units and the time units. All right, so let's start with that. So we have 80 liters per 1 minute. I'll just put MIN for minute. And we're going to multiply this by another fraction that will help us cancel out either liters or minutes. Okay, so I'm going to convert liters first to milliliters. So liters will go on the bottom, ml will go on the top. Relationship between ml and L is 1 liter equals 1,000, aka 10 to the 3 milliliters. Okay, so I'll put 10 to the 3 on the top and 1 on the bottom, because that's what matches here. You just put the numbers that match. Okay, liters go away, leaving me with ml. Very good, that is what I want. I can move on to converting time. So in this new fraction, this will help me convert minutes to hours. Minutes will go on the top because that's what I need to cancel out. Hours will go on the bottom. Okay, and let's see. So in 1 hour, I have 60 minutes. So I'll match up these numbers here, 60 for the minutes, 1 for the hour. Now minutes will go away, and I am left with ml per hour. Okay, so you're just going to multiply everything on the top divided by everything on the bottom, which essentially is just 80 times 10 to the 3 times 60. If you do this, you're going to get 4.8 times 10 to the 6, and that will be in milliliters per hour. Okay, so let's tackle the second part of this question. Okay, so how long in minutes will it take for the pool to contain 850.47 liters? All right, so we know that this pool is filled up with water at 80 liters per minute. So the question becomes, well, how many minutes is it going to take for the pool to have this much water. If we have this many liters that we want, okay, we're just going to divide this by 80 liters per minute. Okay, and we'll just keep in mind that this is in liters, right? Liters are going to cancel out, and we're going to get our number of minutes. All right, and so we get this answer of 10.63 minutes in order to fill up this, pool with this much water. And that makes sense, right? Because if you think about it, if you do it at 80 liters per minute, in 2 minutes, you would expect 160. At 3 minutes, you would expect to be 240 liters in there, and so on and so on. And so if we multiply and double check saying 10.63 times 80, you should be able to get 850.47. All right, so let's move on to isotopes, okay? And in this question, we want to find the number of protons, neutrons, and electrons of iron, okay? And this iron atom has a positive 3 charge here and a mass number of 56. First, let's do the easiest part and find how many protons iron has, okay? So this is for iron. So the number of protons, you just have to look at the periodic table and find the atomic number. Iron's atomic number happens to be 26, so that is the number of protons. All right, and so mass number of 56 means that 56 equals the number of protons plus neutrons, meaning we know we have 26 protons, 26 plus something is going to equal 56. Let's just do some subtraction, right? Subtract 26 from both sides, and you're going to get 30 neutrons. All right, now how many electrons does this iron atom have? Well, it has a positive 3 charge, okay? And so how you're going to calculate this is saying, in total, I know that I need to end up with a positive 3 charge, and this is going to be equal to what you know plus what you don't know. What you don't know is the number of electrons. So you know that protons have a positive charge, so we're going to add 26, and 26 plus whatever number here should give us positive 3. Okay, so we'll do, again, some subtraction and say, okay, we're going to negative 26 to both sides. Okay, and this should give us our number of electrons. Okay, so if you do this math, you should get negative 23, which means we need 23 of the negative ones to make this equation true. Okay, so basically what you're saying here is just saying 23 electrons are needed. Okay, and to summarize, we have 26 protons, we have 30 neutrons, and we have 23 electrons. So if there was any doubt on the last question, let's do another one just in case. So doing the same thing, we need to find protons, neutrons, and electrons for this isotope of bromine, which tells us it has 35 protons and a mass number of 80. All right, so obviously, right, the proton number is 35. Just look on the periodic table or just tell from here. Let's find the number of neutrons. Remember, mass number equals 80, and this is going to be protons plus neutrons. Okay, so protons we know is 35, so 35 plus something needs to equal 80, right? And that thing is 45. So our answer is that we need to have 45 neutrons. Finally, we are going to find the number of electrons. Okay, so looking at this atom right here, there is no charge, meaning that it has a 0 or a neutral charge. Okay, so in the end, we want our total to be 0, 0 charge, and it's going to be what we know plus what we don't know. So we know the number of protons, and we're going to add something to make it 0. So this will be negative 35, which means we have 35 electrons. So to find the number of electrons, you're going to do total charge equal to protons plus electrons. To summarize, for this isotope of bromine, we have 35 protons, 45 neutrons, and 35 electrons. Moving on, let's do some naming problems. So I do have quite a few videos on this on my channel, so you can go look at those later. for more detail. Okay, we're going to write the chemical formula of these things, so calcium nitrate, dinitrogen tetrabromide, and lead 4 oxide. Let's start with calcium nitrate. So calcium indicates Ca, nitrate is a polyatomic ion named, or with the formula, NO3. Now, NO3, okay, one of these guys has -1 charge. Now, calcium has an ionic charge of +2. And I need calcium nitrate to have a 0 charge. At this point in time, if I put one nitrate and one calcium together, I would have a +2 and a -1. This does not equal 0 if you add them up. Therefore, I need another negative to help me balance out this charge of calcium. So if I have two negative things, right, so that's just -1 times 2, okay, equals -2, and then I add 2 to it, I get 0, which is what I want. Therefore, we can say that this is the formula for calcium nitrate. Let's do another example. Next, we have dinitrogen tetrabromide. This is a very, very nice problem because it is a covalent compound, okay, and these prefixes tell us how many of that element we have. So dinitrogen means 2 nitrogens, okay, di is for 2. So 2 of these, and we have tetrabromide, okay, we have bromide or bromine, and we have 4 of them. Okay, so N2Br4 is the formula for dinitrogen tetrabromide. Let's do our final one. We have lead 4 oxide. Okay, lead is Pb, and they're telling us that it has a +4 charge. +4 from this Roman numeral. Okay, oxide. So that just indicates oxygen. Now, oxygen, if you look on the periodic table, has a -2 charge. Now, lead 4 oxide is neutral, just like calcium nitrate, okay? We need the total charge to be 0, okay? And that total charge is going to be made up of this and this, meaning the charge of one part of the compound plus the other part of the compound. So if we put one lead and one oxygen together right now, we have a +4 with a -2. If we add these up, this equals +2, which is not 0. Therefore, we need 2 oxygens, okay? Because if we do that, right, then we would get a -4 from the oxygens, okay? And that would be 4 minus 4, right? So +4 from the lead, -4 from the 2 oxygens, and you would get 0. Okay, so we know that we need 2 oxygens, so let's write that formula. Okay, so 1 lead and 2 oxygens. There we have it, so PbO2. Now we're going to go backwards. Now we're going to be given the chemical formulas, and we're going to find the chemical names next. Okay, so let's start with the first one. What is the name of K2S? K is for potassium, and S is for sulfur, and following our naming rules, we have sulfide, okay? Because we have to add that IDE ending for that element, for the second element. All right, and so K2S is potassium sulfide. We also can kind of know that because it is an ionic compound, and potassium is a main group metal. Okay, therefore no Roman numeral and no prefixes are needed. Let's do another one. So next we have VBr2. Okay, what is V? Well, V is vanadium, and vanadium is a transition metal. Therefore, we need to use parentheses in which the Roman numeral of a charge, right, the charge of vanadium will be placed. Let's go on, though, before we find that. So, second part of this element is Br2. Br is bromine. Now, when we name it, right, second part of the compound is going to have that IDE ending, so it's going to become bromide, okay? Now, let us find the charge of vanadium here. Now, why do we have to do that? We can't get it from the periodic table, so we're going to look at what we do know. What we do know is that bromine has a -1 charge. So 1 bromine, -1 charge. And we have 2 bromines. So that means we multiply this by 2, okay, giving us a -2 charge from bromine atoms. the entire compound charge of VBr2 is 0 because we see nothing in the top right corner. The total needs to be 0, right? So 0 is going to be equal to what we do know. That's charge coming from the total amount of bromines, plus what we don't know. That's going to be the charge of vanadium. Okay, so what goes here? Well, this is just going to be positive 2. So therefore, this one vanadium atom has a +2 charge, written in Roman numerals. So see if you can do the last problem on your own. Alright, so SO3, sulfur and oxygen, these are two nonmetals. That means that this is a covalent or molecular compound. What we do for these is put prefixes. So first we'll just write out the names and then we'll add the prefixes. So we have sulfur, okay, and we have oxide for oxygen. Okay, now we have to add the prefixes. So prefix for 1 is mono, but we do not put mono for the first element. Okay, so this will just remain sulfur. Next, we need to put the prefix for 3 because there are 3 oxygens. What is the prefix for 3? It's going to be tri. Alright, and so sulfur trioxide is going to be the name of SO3. Alright, so let's move on and find the molar mass of lead 2 nitrate. So quickly, we need to find the formula of lead 2 nitrate. Alright, so lead, Pb, and I'm just going to do this really quickly. Okay, we're going to have 2 of these. Okay, so formula for lead 2 nitrate is the following. Okay, next we need to find its molar mass. I have made a video on this again, so you can look back on that for more examples as well. But molar mass essentially means we're going to add up the mass of 1 lead, and then 2 nitrogens and 6 oxygens. Okay, because this subscript is going to be multiplied by the subscripts of whatever is inside of the parentheses. So if there's no subscript here for n, then we're just going to do 2 times 1, because it's implied 1. Okay, but let's do this. So lead, look in the periodic table, alright, and let's see. So lead is going to have 207.2 grams per mole. Then we're going to add up 2 nitrogens. So 2 nitrogens, well, 1 nitrogen has 14.01. That is going to be multiplied by 2, which is going to be equal to 28.02. And finally, we will add up the 6 oxygens, the mass of those 6 oxygens. So do 16 times 6, right? And that will give us 96 grams per mole. Okay, so these are all in grams per mole. Grams per mole. And then we get to add all of this up to get the total mass or the molar mass of lead 2 nitrate. Alright, and then in the end, you'll come out with 331.22, and this will be in grams per mole. Okay, so then this is the molar mass of lead 2 nitrate. How many atoms are in 1 mole of sulfuric acid? Okay, so dealing with atoms or molecules, we know that we need to use Avogadro's number. Avogadro's number for this video is going to be 6.02 times 10 to the 23 particles in 1 mole. Now we need to find the number of atoms in 1 mole of this. So in 1 mole, let's just write out what we have. 1 mole of H2SO4, okay? And what we're going to do here, because, we have to get to atoms, we're going to do moles, 2 molecules, 2 atoms. Okay, and this is all going to be of, H2SO4. Similar to what we did above, I need to cancel out moles, and I need to put in molecules as my new unit. Okay, so moles will go on the bottom, molecules will go on the top, and I will put the corresponding numbers. I'm going to use Avogadro's number and say that there are 6.02 times 10 to the 23 molecules in 1 mole. Moles go away, okay, and we're left with this many molecules. Now, from molecules, okay, I'll just put this here, we need to go to atoms. So how many atoms are there going to be? Okay, so I need to cancel out molecules. So molecules, I'm going to put on the bottom, so I'll just put it here. Okay, and we're going to go to atoms. So in one molecule, okay, so one of these things, how many atoms are there? Just taking this. So we have 2 atoms of hydrogen plus 1 atom of sulfur plus 4 oxygen atoms. Okay, this is going to be 7 atoms in one molecule. Okay, so I want to go to atoms, so I put it here. So that's 7 atoms per one molecule, meaning I should cancel out this and multiply Avogadro's number by 7 to get the number of atoms in 1 mole of H2SO4. So if I do that, I'm going to get 4.214 times 10 to the 24 atoms. How many molecules are there in 25 moles of NH3? NH3, you should be aware, is a polyatomic ion known as ammonia. Okay, so we need to do moles to molecules. So try this one on your own, knowing what you know about the previous problem. Okay, so we have 25 moles of ammonia. Okay, and we would need to go to molecules. So I'll just write Avogadro's number up here for reference. Okay, and our new fraction will help us here convert to molecules. So moles will go on the bottom because we want to cancel that out. Molecules will go on the top. Okay, so what is the equivalence here between moles and molecules? We know that there will be Avogadro's number of molecules in 1 mole. So I'll put 1 for mole, and I'll put Avogadro's number here for molecules. Okay, moles go away, leaving me with molecules, just like I wanted. So now it's 25 times Avogadro's number. The result here is going to be 1.505 times 10 to the 25, and this will be in molecules. Okay, specifically molecules of NH3. Now moving on to a slightly different topic, we're going to find the percent composition of nitrogen in this compound, KNO3. For percent composition, I need to know the mass of nitrogen. Okay, so mass of N times atoms of N. Okay, and this will all be divided by the total mass of the compound, aka the molar mass of KNO3. Let's plug in the numbers. What is the mass of one nitrogen atom? Well, that's just going to be 14.01. How many atoms of nitrogen are there? Well, in the compound, there's just 1, so we'll multiply this by 1. Then what is the molar mass of potassium nitrate? Well, let's see. Potassium has the atomic mass of 39.1. Then we add this 14.01 for nitrogen. Then we add 48 for the mass of 3 oxygens. And we'll just add all of this up. All right, and this will be 101.11. And that will be in grams per mole. Okay, so on the bottom of this new fraction, we have 101.11 grams per mole. So what is the percent composition here? Well, we're just going to do 14.01 divided by 101.11. If you do this, you're going to get 0.139, and that will be the percent composition, okay? Now, in order to get a percent, you just multiply this by 100, okay, and you'll get 13.9%, okay? That's basically the percent that nitrogen takes up from the mass. How many moles are there in 345 grams of carbon dioxide? Okay, so we need to find the number of moles in this amount of grams. Well, we know that the number of moles, okay, is going to be equal to the given mass. Okay, I'll just put given, but that's for mass. And that will be divided by the molar mass of carbon dioxide, because that's the compound we are talking about. Okay, so let's do that. So the number of moles of carbon dioxide that are present, okay, that's going to be equal to, well, what is the given mass? The given mass is going to be 345 grams. What is the molar mass of carbon dioxide? Well, let's just add that up. right? So we have 1 carbon, that's 12.01, plus 2 oxygens, okay, because carbon dioxide formula is CO2. And so 2 oxygens is going to be 32, grams per mole. Okay, grams go away, leaving us with moles. Okay, now we have a nice division problem here. The answer here is going to be 7.84 moles. Okay, and that's going to be of carbon dioxide. Now let's do this problem about finding the molecular formula. Okay, and we're given that the molecular mass of the compound is 110 grams per mole, and we also are given this other information, these percent compositions of the elements, to find its empirical formula. Alright, so for this, we're going to start out by listing what elements we have. So we have carbon, seems we have hydrogen, we also have oxygen. So now what I'm going to do is just write, these equal signs and start putting the percent numbers without the percent sign over the atomic masses of these elements. So what does that look like? Well, they say 65.45% of carbon, so I'm just going to say, okay, 65.45 without the percent sign, divided by the atomic mass of this element, which is 12.01. The same thing goes for hydrogen. Hydrogen says 5.48%, so I'm just going to say 5.48 divided by atomic mass of hydrogen, which is 1.01. Okay, so we'll do the same thing for oxygen. So oxygen is going to be 29.08 divided by 16. Now find the answers to all of these fractions. Okay, so if you do all of these are the numbers you should get. Okay, and our next step is to say, okay, so out of the numbers in blue that we just found, which is the smallest? Your eyes should go here, and what we're going to do to this smallest number is going to be to put it in the denominator of all of these new blue fractions. Okay, so new number is going to be the smallest that we got out of the blue. Okay, and we'll put that under every one of these fractions. Then we have some more fractions to solve. So this is going to tell you, these numbers in green, are going to tell you the subscripts of each element. So in our final formula, right, we're going to have this CHO, right? And the question is, well, how many C's, how many H's, and so on. So this is telling us that we're going to have 3 C's, 3 H's, and 1 oxygen. Okay, so C3, H3, O should be the empirical formula for this question. Now we have another task, and that is going to be to find the molecular formula given the molecular mass. So the difference between molecular and empirical formula is that empirical formula is the simplest formula, okay? The subscripts are very nice and small, very simplified, and the molecular formula has these larger ratios, so not simplified, essentially, okay? So they are kind of multiplied by some common number. So our question is, what is this molecular formula? It still has carbon, hydrogen, and oxygen, but what are the new subscripts? So in order to find out, we need to do this. We need to divide 110, meaning divide the molecular mass by the current mass. So the current mass would be of the empirical formula. So molecular mass divided by empirical formula mass should give you a number, okay? I'll give you a number, and that number you're going to use to multiply each of these little subscripts here. Okay, so our question is essentially, what is the molar mass of this empirical formula? So I'm just going to do this real quickly, okay? Okay, so the molar mass here of this empirical formula should be 55.06 grams per mole. Okay, so grams, these units just cancel out, okay? And we're left with 110 divided by 55.06. So when we do this, we get a number that looks like 1.9978 okay, which this is essentially just 2, okay, so we're just going to round it to 2, it's close enough. And we're going to say, hey, we're going to multiply this 2 by the 1 for the subscript of oxygen, by 3 for the subscript of hydrogen, and by 3 again for the subscript of carbon. So let's go and get our new subscripts. So 2 times 3 is 6, 2 times 3 again is 6, 2 times 1 is 2. Therefore, our molecular formula should look like this: C6H6O2. Thank you so much for watching this video, everyone. I really hope you found it helpful. If you did, please consider subscribing, liking this video, and commenting down below. Now, that is it for today, and I will see you next time.